Welcome to our tutorial on Jfet, and in this tutorial we're going to discuss today about the Jfet characteristic curves. Okay, so there we go. We have the Jfet characteristic curves on our agenda of discussion today. Okay, so we'll just start our day with the first characteristic curve over here. That's the static characteristics of the Jfet. Okay, so in the static characteristics we need to construct, or rather need an experimental setup for studying the static characteristics over here, and I'll just show you the required experimental setup over here. So just hold on for a second there. So there it is. That's the diagram for the required amount of experimental setup, okay, for studying the static characteristics over here. So you can get to see this circuit over here where we have our Jfet device, okay, fitted with a number of measuring instruments over here. So there we have the voltmeter V1, okay, in order to measure the amount of gate source voltage, that's VGS, and then we also have the voltmeter V2 on the other side to measure the amount of the drain source voltage, VDS, and then we also have from this voltage source VS2 a current entering into the Jfet channel through its drain terminal. So we just call this current as the drain current, okay, denoted by the symbol ID, okay, and this ammeter over here would just measure the value of the ID, that's the drain current, okay, entering into the Jfet. Okay, so in this experimental setup we're just gonna keep the gate source voltage fixed at a particular value, okay, and for a given value of the gate source voltage we're gonna measure the variation in the drain current with respect to the variations on the drain source voltage. So basically we're gonna vary the voltage on the voltage source VS2 basically, and then just study the amount of variation in the drain current with respect to all the variations in the drain source voltage. I'll just show you the static characteristics in a short while. Just hold on for a second, please. Okay, so yeah, that's the required diagram for the static characteristics, as you can see over here. So as you can see from this diagram, basically what we have here is that this graph that I'm just showing you in this case represents the static characteristics of the Jfet. Okay, so you can get to see this whole characteristic basically being divided into three regions. The first one is the linear region over here, where you can get to see that the drain current, okay, so the static characteristics is basically a graph between the drain current versus the variation in the drain source voltage. Okay, so you can get to see over here that in the linear region over here the drain current, okay, varies linearly with the variation in the drain source voltage. So over there the drain current is directly proportional to all the variations in the drain source voltage, and that's where it gets its name, the linear region. Okay, this happens, or rather the linear region is achieved at lower values of the drain source voltage. So I'll just show you what happens inside the Jfet when it just operates in the linear region. I'll just be showing you a diagram over here just in a short while. Just give me a second there. Okay, so here is the required diagram, okay, depicting the phenomena inside the Jfet while it's operating in the linear region basically. So you can see here under lower values of the drain source voltage, okay, so here we have lower values of drain source voltage, okay, so lower values of VDS. Now under this case we can get to see that there is a very little amount of depletion region that is just formed inside the channel. Okay, so this shaded regions inside the channel in pink gives us the depletion regions that are just developed inside the channel of the Jfet. Okay, so here you can get to see the depletion region, which is doesn't extend too much deeper into the channel. Okay, so that's the the channel through which the drain current would basically flow. So the channel has effective, or rather sufficient amount of clearance. Okay, it has a sufficient amount of channel width to actually let the drain current increase through just drain current flowing through itself increasing under a higher value of the drain source voltage. So that's basically what happens over here. If we just go on increasing the drain source voltage, we can get to see that the drain current would basically increase during this case, okay, until a specific level of VDS. So there you go, that's the specific level of VDS till which we can get to see this characteristic of the Jfet. Okay, so I'll just show you what happens after this by means of another diagram. Just hold on for a second, please. Okay, well, I just show you this diagram over here. Okay, so there you go. Sorry there for the inconvenience caused. Okay, so just kindly don't mind at that. Okay, so basically where we left the discussion, I'd just like to enter it, or rather resume it from there on. So basically this is what basically happens when the saturation when we just come to the end of the linear region. Okay, so as I said that the linear region would just extend till a certain extent of the voltage, a certain extent of the the drain source voltage, where if we just go on increasing the value of the drain source voltage, will enter into a state where the drain current would just stop increasing further linearly with the variations in the drain source voltage. So that is exactly what it's depicted over here in this figure. We can get to see over here that the depletion regions, as you can see, extending much deeper into the regions closer to the drain terminal. Okay, I mean almost meeting with each other at a particular point right over here. So as you can see that the depletion regions are not symmetrical. Okay, they're not uniform throughout the length of the channel, and it's due to the fact that because of the effective amount of reverse bias voltage that exists across this gate and channel junction right over here is not the same everywhere throughout the length of the channel. This reverse bias this reverse bias voltage existing across the gate and the channel junction is less towards the region inside the channel, okay, closer to the source terminal, and it's more towards more over the regions closer to the drain terminal. Okay, so basically what happens is that the gate channel reverse bias voltage being higher at the regions closer to the drain terminal, okay, the depletion region naturally penetrates deeper into the channel right at the regions closer to the drain terminal. So over here we can see for a particular value of that of the drain source voltage, we can get to see that the drain current, or rather the depletion regions would just meet up almost. Okay, so they'll just almost meet up at this point over here. So here we would be having a very narrow gap. Okay, so there would be a very narrow gap over here. Okay, so through which a certain value of the drain current would just be passing through. So over here at this point, as you can see, that's depicted here in red, this just gives us the value of the saturation voltage. Okay, so here we can get to see that for a under the zero voltage of gate source voltage over here, so under value of gate source voltage equals to 0 volts, okay, the point, or rather the voltage, the value of drain source voltage, okay, at which the current would just saturate itself, would be referred to as the pinch off voltage. Okay, so in this diagram that I'm just showing you over here, where the depletion regions almost meet up with each other, causing a very narrow gap existing between them, is just referred to the condition of pinch off. So this is the phenomena of pinch off that occurs inside that of a Jfet. Okay, so at this moment the depletion region almost meet up with each other, and the channel width, as you can see, is not sufficient to allow further increase in the amount of drain current, or rather in the magnitude of drain current with increasing values of drain source voltage. Okay, so at this moment what happens is that the drain current basically saturates, or rather stops increasing at a particular value, and it'll just remain over there throughout as we go on increasing the drain source voltage throughout. So we can get to see after the pinch off occurs over here, no matter how much we increase the drain source voltage, the drain currents would remain fixed at their particular values. Okay, so you can get to see that the as the gate source voltage, I mean as the reverse bias voltage on the gate terminal, that's the gate source voltage, as we just go on increasing the reverse bias on the gate source voltage, okay, we can get to see that the saturation values of the drain current just drops with each of the increase in the gate source voltage over here. So basically, keeping that in mind, I would like to show you another diagram where I just exhibit this phenomena. It should be up shortly by now. Just give me a second there. Okay, so there you go. That's the diagram that I was just thinking of showing you over here. So you can get to see in the diagram number 3 that upon increasing the value of the drain source voltage further, okay, we can see that the amount of depletion region, okay, the extent of depletion region inside the channel increases a lot, and almost the whole length of the channel gets covered in the depletion region. Okay, so you can get to see the depletion region extends throughout the channel. Okay, so it extends throughout the channel. Okay, so there you go, throughout channel, right? So over here, as you can see, that the depletion region almost makes it throughout the channel, okay, and that the channel width is almost not sufficient for allowing any further increase in the value of the drain current. So under this case, we get, or rather we just say that here in the previous diagram number 2, the Jfet entered into saturation, and this happens further deeper into the characteristics whenever we have high values of the drain source voltage. So this basically takes place at high values of drain source voltage basically. So after this, what happens is that the characteristics enters into the breakdown region, where we can get to see that the drain current just suddenly increases with under a increased value of drain source voltage. So what happens in this case is basically that whenever this sort of stage, I mean the stage 3 is reached over here, if we just go on increasing the value of drain source voltage throughout, then the gate channel junction breaks down, okay, and the depletion region that was primarily devoid of charge carriers, so this is the depletion region devoid of charge carriers. That's exactly what the depletion regions are primarily, but in this case, okay, under high values of the drain source voltage, what happens is that breakdown, I mean avalanche or Zener breakdown basically occurs inside the depletion regions, thereby freeing electron hole pairs. Okay, so now the unipolar Jfet, okay, under this circumstances becomes a bipolar device. Okay, so since there are two types of charge carriers over here, both the electrons and holes, that is. So now, due to the sudden increase of the amount of electrons and hole pairs in the channel region, we can get to see a sudden surge in the value of the drain current. Okay, so also from the characteristic we can see that for lower values of gate source voltage, okay, the breakdown voltage, that's the values of VDS over here, which at which breakdown would occur, is referred to as the breakdown voltage. So the breakdown basically occurs at lower values of the drain source voltage when the gate source voltages are lower, as you can get to see over here. So upon increasing the reverse bias gate source voltages over here, we can get to see that the breakdown occurs at lower values of drain source voltage from these characteristics. Okay, and also we can get to see the pinch offs, okay, occurring, I mean the current saturates at a lower value of the drain source voltage when the amount of reverse bias voltage on the gate terminal is higher. So for higher values of reverse bias gate source voltages, we can get to see the currents, okay, I mean the drain currents saturating at lower values of the drain source voltage. So that's exactly whatever we can get to see from this characteristics over here. Okay, that gives us an idea that upon increasing the gate source voltages, you can get to see from this characteristics that the drain current would basically decrease in magnitude. Okay, so now this phenomena basically gives rise to it just gives rise to the other type of characteristic over here, referred to as the transfer characteristics. So under the transfer characteristics, what we what we just try to show is that we just try to plot the or rather just try to show the variation of the drain current, okay, with respect to variations in the gate source voltage. So that's why it's just known as the transfer characteristic, as it just relates the output current with the input gate source voltage basically. So you can get to see the transfer characteristics for a JFET, okay, would appear something like this. Okay, so here if you all would take a look at this graph over here, then we can get to see for sufficiently large values of reverse bias voltages at the gate source terminals, okay, we can get to see that the current, I mean the drain current, that is approximately becomes 0 for a sufficiently large values of gate source voltage, okay. And at the for 0 values of gate source voltage, I mean when the gate source voltage is almost 0 over here, we can get to see the drain current, okay, attaining its maximum value. So I'll just call it ID max. So the drain current is maximum under a 0 value of gate source voltage. I mean the drain current is maximum when the gate source voltage is just 0 volts, okay. In other case, whenever we just go on increasing the gate source voltage, I mean thereby increasing the amount of reverse bias on the gate terminal, we can get to see the drain current just reducing down approximately to 0 volts, okay. So this is basically what we see here in the transfer characteristics of the JFET. Okay, so that's all we have from the this tutorial on JFET characteristics. Hope you would like our show further on the JFET tutorials. Don't forget to watch them, and thanks for watching this tutorial, and goodbye for now.